Now, you might have been wondering why on earth we looked at inverse functions yesterday. We're in the middle of this topic of trig. Why do inverse functions? So we can create these new set of functions, the inverse trig functions. Now, the problem with trig functions is they're periodic. So they're all going to fail the horizontal line test. So none of them actually have an inverse function. We're going to have to restrict the domain in order to create one. So let's do sine first of all. So inverse sine of x comes from the basic curve of sine x. So let's draw that in. So there's y equals sine x. Now at this stage the domain is all real x. The range -1 to 1, we know that. But fails the horizontal line test, doesn't have an inverse. So we want to pick a piece of the curve that's continually increasing or decreasing. Ideally, we'd like positives and 0 if we can, and try to capture the whole range. So when I look at those pieces of criteria, the logical one to pick would be going from -π/2 to π/2. That would get the complete range. I'm going to have 0, and I'm going to capture some of the positives as well. So my range does not change, so that's good. So my new function, y equals the inverse sine of x, domain and range are going to swap around. So the domain is now going to be -1 to 1, and the range will be -π/2 to π/2. We know it'll be a reflection in the line y equals x. Now, because of the scale I've done on this graph, my scale on the y-axis is very different to the scale on the x-axis if you look at it. I'll just redraw it to the side of just what our inverse sine curve will look like. But basically it's the piece of the sine curve, but it's winding along the y-axis instead of the x-axis. So it looks something like that. We can see then from the picture is it's an odd function. And that's what we said yesterday. If you find the inverse of an odd function, it should still be an odd function. So indeed, that's what we've got. Okay, let's have a look at inverse cos. Do the same thing. Draw up the original graph, y equals cos x. Domain or real x, range -1 to 1, and fails the horizontal line test. So we want to restrict our domain. We want to get a piece that's continually increasing or decreasing. Include 0 if we can, and positives if we can. So for this one, I'm going to go from 0 to pi. I'll get the complete range, and it'll satisfy those things. So the range is still -1 to 1. So my inverse, they'll swap around. Domain -1 to 1. Range will now be 0 to pi. Again, we would reflect in y equals x, and we would end up with something like this. And what we saw yesterday is we said an even function won't be even when we find the inverse, and sure enough it's not an even function. We haven't ended up with an even function. Tan, let's have a look at that one. So y equals tan x, draw up the original curve, fails the horizontal line test again. Domain was that strange one where I had to write in all the multiples of pi after π/2. The range is all real y, no inverse. So again, pick a piece of it. Well, the logical one here is to go between two of the asymptotes, and we'll get the complete range. So I'll go from -π/2 and π/2, but notice we don't include π/2 for this one because they're the asymptotes, they're not part of the original domain. The range will be all real y, so now they'll swap around for inverse tan. My domain will end up being all real x. My range will just go between -π/2 and π/2. Reflect it, and again, we can see the original one was an odd function, and the inverse turns out to be an odd function as well. So there's the three basic inverse trig graphs. What can we use these graphs for? We can see things now. Well, because inverse sine is an odd function, that means inverse sine of -x must be the negative of the inverse sine of x. So that comes from the fact that it was an odd function. Inverse cos is a little bit different because it's not odd or even. It ends up being this relationship. The inverse cos of -x equals pi minus the inverse cos of x. And the reason for that is it's an odd function if you look at it, but it's been shifted up π/2. It has rotational symmetry, but not around the origin, but around π/2. And I'll show you in a sec how we can get that. Inverse tan we saw was an odd function. So inverse tan of -x is minus inverse tan of x. And the last one here is this, inverse sine of x plus inverse cos of x will always be π/2. That comes from the angle sum of a triangle. Let's go and show you how that inverse cos one. There's the inverse cos graph. If I shift it back down so it becomes an odd function, Well, that new graph would be inverse cos of x minus pi on 2. I've shifted it down pi on 2 units. Now it's an odd function. So function negative x will equal negative function x. So if I substitute in negative x, I'll get inverse cos of negative x minus pi on 2 is the negative of inverse cos of x minus pi on 2. Move that minus pi on 2 to the other side and we get the relationship that we've got there. So that's where it comes from. Sort of to do with the fact that it's an odd function that has been shifted. Some other ways you can write inverse sine of x. I personally prefer the first one. It's also the notation you'll find on your calculator as well, those buttons. But you do sometimes see people write arc sine instead of sine with the negative 1 there. I guess that's just so we don't get confused because negative 1 is not a power. And you remember when we were doing trig identities, if we wanted to square it, we wrote it as sine squared x with just a 2 there. But this does not mean 1 over sine x. It's not saying to the power of negative 1. You see, that's why we have those reciprocal ratios like cosecant and secant and cotan, because we don't use negative indices when it comes to trig. So that negative 1 means inverse sine. And another even shorter way of writing is a sine. Very rare. I don't see it that often at all. You might see arc sine a bit more. I know they've used arc sine in the HSC in the past as well. Okay. Do some examples. So we've now got to find the exact value of this. Remember, inverse tan or any inverse trig is an angle, right? Because it's going back from the trig ratio to what angle gave me this answer. So that's what this is saying. What angle gave me the answer of root 3? So the tan of what is root 3 minus the tan of what is what? There are a couple of exact values. So it'd be pi on 3 minus pi on 4. Bit of fraction work there, we get pi on 12. Inverse sine of 1 on root 2 minus the inverse sine of minus a half. So same idea. It's going to be pi on 4 minus, now inverse sine of minus a half. Because we restricted the domain, then we're only looking for answers with the inverse sine graph that's either going to be in the first quadrant or the fourth quadrant, because our graph was that. So we're either going to get an acute angle or a negative acute angle. That's where the graph existed. So we don't have to worry about, oh, which quadrant is it in? If it's negative, then I must get a negative acute angle for inverse sine. If it's positive, I get a positive one. A half, we know the angle is pi on 6. So for this one, it must be minus pi on 6. So pi on 4 minus pi on 6, and we get 5 pi on 12. The cosine of the inverse sine of 40 on 41. So cosine of an angle, that angle is the inverse sine of 40 on 41. How do I do this one? Well, I draw myself up a triangle to try and get my head around it. So they're saying there's an angle, so I'll just label one of them, where the inverse sine is 40 on 41. So opposite over hypotenuse is 40 on 41. Do a bit of Pythagoras, the other side is 9, and so now I can just read off the triangle. Well, the cosine of that triangle would be 9 on 41. And there's my answer. Go back the other way. The inverse sine of the sine of 5 pi on 6. So the sine of 5 pi on 6 would give me a ratio, and then we're saying the inverse sine of the ratio, which angle would it be? Now, it's very tempting, because inverses cancel each other out, to just say, oh, the answer is 5 pi on 6. But if you go back to the graph, 5 pi on 6 is not in the domain. So the answer to this one is actually pi on 6. Now how do I know it's pi on 6? Well, 5 pi on 6 is in the second quadrant. So in the second quadrant we know sine is positive. Which acute angle would it be in the second quadrant? Well, in the second quadrant it was pi minus the acute angle. So pi minus what gives me 5 pi on 6? Pi on 6 does. So pi on 6 is the answer for that one, not 5 pi on 6. You always got to go back to what does the graph look like? Which quadrants are we in? That will give us the correct answer. So 17b is playing around with these inverse trig functions.